Hi everyone, welcome to this lecture. Today I would like to talk about an interesting topic regarding how precipitation works for the isolation of EV. I will frequently cite the term of MOOC, which is minimal information for studies of extracellular vesicles. MOOC was published by leading scientists from the International Society for Extracellular Vesicles. This document is very helpful for standardizing and optimizing our EV researches. When we talk about EV purity, I would emphasize a parameter called particle-protein ratio, which measures how many particles per microgram protein in a certain EV isolation. We know that high abundant protein contamination is a major concern for EV isolations from many sample types, including serum plasma, urine, and other protein-rich biofluids. For these sample types, we expect to remove as much as high abundant proteins to increase the EV purity, which gives a higher particle-protein ratio. For EV enrichment, we expect to see increased EV purity after a certain isolation. The EV recovery represents the percentage of total EVs preserved after isolations. So there are three most common technologies for the precipitation-based EV isolations. First, some polymers can form mesh structures to help EV to aggregate based on excluding volume theory. So PEG is one of the most widely used excluding volume polymers. Second, positively charged reagents could neutralize the negatively charged EVs to allow precipitation. So pertamine is one example. Third, organic solvents such as TCA and acetone can precipitate proteins and leave EVs in solution. This technology is also called PROSPER. So first, let's look at the volume-excluding polymers. Precipitation is typically rapid and efficient. EVs could be obtained within 60 to 120 minutes, starting from the sample pre-treatment. After mixing samples with reagents, some methods also allow overnight incubation. According to papers published by Professor Yan Xiaomei's group and others, PEG method has a very high recovery rate, typically over 80%. This is much higher than the EV recovery rate of ultracentrifugation, that is around 40%. However, for sample types such as plasma serum, it should be kept in mind that precipitation can co-isolate a phenomenal amount of lipoprotein particles and aggregated proteins. In addition, precipitation will bring in reagent contaminations that may affect subsequent analysis. Excluding volume polymer is a special term in polymer science. To be accurate, it refers to the idea that one part of a long chain molecule cannot occupy space that is already occupied by another part of the same molecule. For example, in dilute condition, we can see that the chain of this molecule forms a hollow structure, and the green circle represents the excluded volume of this molecule. Such hollow space can be taken by another molecule such as protein. When molecules become crowded, a mesh structure with many hollow spaces can be formed. Such a mesh can capture bigger particles such as EVs. So PEG is one of the most commonly used volume-excluding polymers for EV preparation. According to how many ethylene molecules polymerize, PEG has diversified molecular weights. While those with the molecular weight ranged from 6,000 to 20,000 Daltons are frequently used for EV precipitation. So PEG is negatively charged and hydrophilic, which means that they are soluble in water. PEG with proper concentration can form mesh structure to capture particles, which leads to their aggregation. After aggregation, it is very easy to harvest particles with low-speed centrifugations. PEG method has a very high EV recovery rate, typically over 80%. However, when dealing with protein-rich biofluids, it has an intrinsic problem of low purity. For example, in blood plasma, the purity is typically less than 1 of 10 to the 9th particles per microgram protein. So in comparison, ultracentrifugation and size exclusion chromatography can reach 6 of 10 to the 10th particles per microgram protein. So in practice, PEG is very easy to use. Typically, we need to remove cell debris with sequential low-speed and high-speed centrifugations. Samples are then mixed with PEG solution to reach final concentrations from 5% to 8% of PEG, followed by incubation at 4 degrees. Incubation time could range from 60 minutes to overnight for different sample types or based on different laboratory protocols. EVs will be captured and aggregated by the PEG. After that, particles can be harvested through very low-speed centrifugations. In addition, PEG has been shown to be potentially scaled up for industrial applications. Another group also suggested biphase methods to use low concentration of PEG and dextrin to separate EVs from proteins. It is also called the aqueous two-phase system, ATPS. Here, diluted PEG will retain protein in the PEG phase, and dextran will keep the EVs in the dextran phase. This method shows a protein removal rate of over 95%, while it has an over 70% of EV recovery rate. It is nice that the incubation time of this method only requires 15 minutes at 4 degrees. But in EV studies, we have to take co-isolating contaminations into account. So, for example, your human plasma, the most common contaminants are high abundant proteins like albumin and lipoproteins. In this figure, we can see that chylomicrons are very low density lipoproteins and low density lipoproteins and protein particles have similar size distributions to EVs. In addition, high density lipoproteins and viruses have very similar densities to EVs too. Particularly, lipoproteins particles have striking interference with the EV purity. Although with their donor difference, it has been estimated that in human plasma, an EV particle is mixed with around at least 10 million lipoprotein particles. So if lipoproteins are not removed sufficiently, some conclusions of EVs could be misled by lipoprotein contaminations. So as a good example published in this JEV paper, the authors used PEG to isolate the EVs from rat plasma. They found that PEG EVs are highly contaminated with albumin and lipoprotein. So another example is for size exclusion chromatography. So as you see, usually fractionate a sample into typically 26 fractions. And the EVs are highly enriched in the 6th to 11th fractions. And the later fractions enrich proteins. In this figure, we could see that microRNAs are equally abundant in the EV and protein fractions. This suggests that if we are focusing on EV microRNA detection for some diseases, protein contaminations will bring non-EV microRNAs into the research conclusions. As such, quality control is very important for EV alone or EV combinations with other methods. As suggested by MOOC 2018, size distribution of EVs should be made clear. For example, when we look into the small EVs, 30 to 200 nanometer EVs should be enriched. In addition, EV markers such as integrins and CD9, as well as co-isolating contaminants, should be evaluated quantitatively or semi-quantitatively. We should also control the EV purity for each isolation to make valid comparison between technological repeats. To generate reproducible data, several aspects should be minimally reported for the PEG-EV isolations. These include PEG molecular weight and concentration, sample time, incubation time, detailed instrumental settings for nanoparticle tracking analysis or other systems. I would also recommend to refer to the latest version of MOOC for further information. So in summary of the practical information, the PEG method requires only 1.5 hour in minimum to complete each isolation. And it allows a large number of isolations performed in parallel. Although currently autosampler seems not be commercially available, but it is promising that we can expect that. And PEG method can be easily scaled up for industrial applications. But when we perform in vivo analysis or pursue in real-time monitoring, PEG method seems not to be applicable. So let's move on to see the charge-based precipitation. An EV has a phospholipid bilayer membrane. When we look at a single phospholipid, it has a negatively charged head, which is hydrophilic or water-loving. And the two fatty acid tails are very nonpolar, which is hydrophobic or water-fearing. So the inside and outside of the membrane are all negatively charged. In addition, there are abundant phosphatidyl serum PS on most of the EV membrane. So we know that PS is also negatively charged. So due to the electrostatic repulsion, EVs tend not to aggregate with each other. However, if we neutralize the EV charge, it will lead to EV's aggregation, which is called charge-based precipitation. Protamine and sodium acetate are commonly used in the charge-based precipitation. Here, both reagents are alkaline and could easily neutralize the EV negative charge and cause them to precipitate. However, nearly all lipoproteins are negatively charged. So lipoproteins have phospholipid monolayer in their structure. The neutralization of EV will with either protamine or sodium acetate will also cause lipoprotein to aggregate. Thus, this strategy suffers from severe co-isolating contaminations too. So the third strategy is Prosper. It shows much better performance to remove proteins. The working principle is quite straightforward. Prosper uses acetone to cold precipitate protein while leaving EVs in solution. So with speed vac or ultrafiltration, EVs could be further harvested or concentrated. So in this paper, the authors showed that Prosper could obtain EVs with even higher purity than ultracentrifugation. For example, they show they have Prosper EVs have higher CD9, CD63 Alex, and CD81, and so on. Especially, these simple methods showed a very nice performance to remove lipoproteins and albumin. But there are past publications suggest that the recovery rate of PRASPR tends to be lower than other methods. While it may cause EV fusion or affect the EV physiology. Indeed, this is a promising method in the EV field that warrants further validations. So in my opinion, most precipitation methods are of obvious advantages. They are quick, easy to operate, and with high EV yields. In addition, they do not need major instruments, which is very important for clinical applications. But when we claim findings in the EV field, we still need to refer to MOOC to make confident conclusions. I would thank you for your attention, and you are more than welcome to listen to other lectures organized by the Educational Committee of ISEV. Thank you again.